Hi and welcome to my YouTube channel, Spacetime Diaries. In this first video of our new series, Mathematical Topics in Physics, I'm diving into the fascinating world of vectors. We all have some basic understanding from our early school days about vectors, the fact that we can add them together to form new vectors and that we can multiply them by numbers to scale them. This little insight forms a powerful foundation that lets us generalize and apply similar concepts to many other things around us. Whether we are studying physical forces, computer graphics, or even abstract mathematical concepts, the idea of vector operations helps us see patterns and relationships in diverse contexts. Let's consider a set V that satisfies two fundamental operations. When you add any two objects from V, the result is still an object in V. When you multiply any object in V by a number, the result remains in V. Even without any additional restrictions, these two properties capture the essence of how vectors behave. This simple structure forms the backbone of what we call a vector space in mathematics and physics. It is this very idea that allows us to generalize the concept of vectors beyond just arrows in space, extending their use to a wide range of applications. Furthermore, there are two additional axioms that must be satisfied. First, the addition operation must be commutative, meaning that the order in which we add the objects doesn't affect the outcome. Second, the operation must be associative, which ensures that no matter how we group the objects when adding them, the result remains the same. The set must also include zero element, often called the additive identity, such that when it is added to any object in the set, the object remains unchanged. The zero element essentially defines the origin of our space. Finally, every element in the set must have an inverse within the set, ensuring that when any element is added to its inverse, the result is the neutral zero element. Any set that satisfies these axioms is called a vector space, and the elements within the set are referred to as vectors. Now let's explore an example of vector space using colors. In the RGB color model, colors are generated by combining different intensities of red, green, and blue. Here we can think of red, green, and blue as the unit vectors of our color space. Just as any vector in 2D or 3D space can be expressed as a combination of its unit vectors, any color we perceive can be formed by combining red, green, and blue in varying amounts. This concept works because human eyes are sensitive to these three primary colors. All the other colors we see are simply various mixtures of red, green, and blue. The RGB model is a practical example of a vector space, where each color is a vector created by combining the base's elements. We usually define position vectors in 2D Cartesian coordinate systems as a difference between 2 points. And in fact, that again is a decent method to build a vector space. Here you see 2D Cartesian coordinates, and the set of all position vectors in 2D form a two-dimensional vector space. An interesting example of vector space is a set of functions, and some of these interesting spaces are sometimes infinite dimensional, and they are very important in quantum mechanics. Now, although I've used the word dimensions in our examples, the formal definition of a vector space doesn't actually mention dimensions. So where do dimensions come in? They emerge from the structure of the space rather than from its axioms. We define the dimension of a vector space as the minimum number of vectors needed to span or generate the entire space. In the case of familiar vector spaces, these vectors are often the standard unit vectors like I, j, and k. Essentially, the dimension tells us the number of independent directions within this space. For one-dimensional space, we need one vector, and we can generate all the other vectors by multiplying different scalars with it. We can add even more structure to a vector space by defining an inner product. An inner product is a function that takes two vectors from the space and returns a real number. For it to be well defined, it must satisfy the following axioms. The inner product is symmetric, meaning the order of the vectors doesn't matter. In other words, Inner product of u with v and v with u is equal. The inner product is linear in at least one of its arguments. This means that it distributes over vector addition and interacts predictably with scalar. Finally, the inner product of any vector with itself is always non-negative, and it is 0 if and only if the vector is 0 vector. This relational structure allows us to measure angles and lengths within the space, paving the way for deeper geometric insights and applications in physics and engineering. It is this feature that endows a vector space with true geometric meaning. Without it, a vector space is purely an algebraic concept. That wraps up today's exploration into the structure of vectors and vector spaces. If you think of any phenomenon or system that might be modeled as a vector space, please drop your ideas in the comments below. Don't forget to like, subscribe, and hit that notification bell. Thanks for watching, and until next time, keep exploring the universe.